All right, first thing we have to find for this one is the length of a vector AP in terms of lambda. So the first thing we need to do, of course, is find vector AP. So we need both the point P and the point A. We are given a line L is that P is a variable point on that line. So any point on that line would have the position. So P is a point. So we just put it in, so -2 plus lambda, 1 plus 0 lambda, and then 2 minus lambda. So just reading off that as a point, any point, right? And then A is the point 1, 1, 1. So if I find, first of all, the vector AP, we're going to take the P part, and we're going to minus A, so they're all -1, so that's pretty easy actually. So rather than waste my room here, I will just write it, although I'm wasting my room now. So -2 plus lambda minus 1, that would be lambda minus 3, or -3 plus lambda. Then I've got 1 minus 1, that's 0. Then I've got 2 minus lambda minus 1, which is 1 minus lambda. So then if I want the distance of that, I am going to square root lambda minus 3 all squared, 0 squared, and 1 minus lambda all squared, which would give me lambda squared minus 6 lambda plus 9, 1 minus 2 lambda plus lambda squared. Putting all that together, we should get 2 lambda squareds minus 8 lambda and a positive 10 there. So that's the distance. So then when it says hence for B, find the minimum distance from A to L. Remember, L is just the line and A is the point 1, 1, 1. So AP is a point on that line. So we've already got the distance, but we want the minimum distance. So we want to minimize that equation. Now, there's a couple of ways to do that. We could do it by observation. So by observation, you can see that if I put a 2 outside here, I'm going to have, so that would be a -4 lambda. So if I square that, I'm getting the lambda squared with the 2 in front, -4 lambda with the 2 in front, so -8 lambda. I'm also getting a +4 with the 2 in front, so that's a +8, and I need 2 more to make that 10. So you can see, if I want to minimize that, the smallest value of that I can make that is if I put a lambda in that makes that whole first term 0, which would be lambda equals 2. Otherwise, I'm going to be adding something on to that +2 and making it bigger. So by observation, I can see that to minimize it, I would make lambda equal 2. And then if I did sub that in, I would get a distance, AP, being just √2. So that would be the minimum distance. Another way to do it is actually just minimize that equation, the actual equation. So where can I find room to do that? So if I look at the actual equation, and of course the square of the distance, if I minimize the square of the distance, it's the same as minimizing the distance. So if I just look underneath, so think of it, oh, I don't know why that's like that. Think of the equation as 2, we just want that, don't we? 2 lambda squared minus 8 lambda plus 10. And if we think of it like finding stationary points, and so we'd set that to 0, you would see lambda equals 2. So you just have to check that that's a minimum, not a maximum. But we know from the equation that this would be a happy parabola. So it is definitely a minimum. So putting lambda equals 2, so you can use calculus as well to minimize that distance. All right, so that's a minimum distance. Now they want us to repeat it and do it a different way, using the dot product of AP and the direction vector L as well. So, alrighty, so let's do that then. So if I look at vector AP, let's see, so I've lost vector AP, but hopefully you've written it down and you can see that vector AP, I probably need that and shouldn't have rubbed it out. So vector AP is -1, 0, -1. So just check that that's what you've got, -1, 0, -1. And this is harder to rub out than the other board, but the other board is not working, sorry. Okay, so we know the direction of line L, there's the direction of line L, and we also know that vector AP is -1, 0, -1. All right, so if we have a look at that dot product, it should be show the minimum distance found in B, sorry I wasn't reading it properly, is the perpendicular distance. Alright, so if we do the dot product of those two, we should get 0 if it's perpendicular distance. Alright, so we've got 1 times -1, which is -1, 0 times 0, and -1 times -1, so that gives you 0. So you can show the dot product of the direction of L and the vector AP is 0, so therefore yes, that shortest distance that we found, this is if lambda is 2, I think lambda is 2, yep, is definitely the perpendicular distance. All right, I hope that makes sense. Okay, so then for D, this is where we want to do it a different way. So if we recognise and we can use the fact that the shortest distance is always the perpendicular distance. So we should actually use that rather than, you know, muddle around. So we know that AP dotted with the direction, the L direction, actually dotted with the L direction, we know that that has to be 0. So if I go back and say I hadn't found that lambda equals 2 yet, so I'd just use the AP that we had with lambda in it, rather than popping in the 2. So that would be lambda 1 minus lambda, or lambda minus lambda plus 1, either way. So if we dot product that with the direction of the line, we would be getting 3 plus lambda minus 1 plus lambda, which gives us -4 plus 2 lambdas. We know that has to equal 0 because it's got to be perpendicular. So again, we can say, oh, lambda must be equal to 2. All right, and then if lambda is equal to 2, we could pop it back into here and we would get AP being -1, 0, -1, and the distance of AP being square root of -1 squared, 0 squared, and -1 squared, which does give us that root 2. So we'd still get that root 2 just looking at a different way. All right, and let's look at it one more way. So this time by choosing point B on the line and finding the length of the projection BA onto L. All right, so when you're doing it kind of geometrically, I find it handy to have some kind of picture, just so you can visualize what you're doing. So what we're having a look at is we've got this line L, and we know the shortest distance from A to L is the perpendicular distance, but we're going to choose another point, B, on line L, and that will help us find this distance using a projection. So if we're using a projection this time, we just want the scalar projection, not the vector projection, because we just want that distance. But anyway, we'll get there, we'll figure that out. All right, so let's pick at any point on that line. Let's just pick this one because that's when lambda is 0. So let's say B is -2, 1, 2, and we know A is 1, 1, 1, and we can then find AB. So whoops, I'll just find AB and put it up here. Okay, so vector AB, we take B first, so -2 and then -a. So -2, -1, 1 -1, and 2 -1. So there's AB there. What is the distance AB? So we're just going to do the square root of our 1 squared. Did I do AB incorrectly? Let me just check. So it was a -2 -1, so that was a -3, yeah, up there. So hopefully you caught that. So we've got a 3 squared, a -3 squared, a 0 squared, and a 1 squared. So we've got a root 10 for that distance there. So I'll put it on the picture. There's a root 10 for that picture, that distance, AB. All right, so we also want to find that angle, because once we've found that angle, if we use cos theta, where will I write it? Cos theta can't always, would be distance, height would be root 10. So we also know cos theta using our formula booklet. We've got our u dot v being equal to our length of u, length of v, cos theta. So if I rearrange that, I've got my cos theta also equaling u dot v. In this case, the direction vectors of each of u and v, which would be this and this. So we know the direction of our AB already, because we've got it up here. So we've got either, I'm going to change it to 3, 0, -1, so I'm just negating it, which is fine. Doesn't matter which direction I go in, the positive or negative direction. So u dot v, now v, our direction comes from the direction of the line, so 1, 0, -1, on the lengths of each of those. So the length of this one, we already know. We know this one's root 10, and this one here, we can use our, okay, so I've got root 10, and if I look at this one, I've got the square root of 1 squared plus 1 squared, so that's square root of 2. So if I equate these two, so this is by derivation, you might just be using a straight formula, and that's fine as well. So by derivation, when I do that dot product, I get 3 plus 1, so I get a 4 on a root 10, root 2, and on the other side, using this one, I get d on root 10. So actually those root 10s will cancel, and the distance will be 4 on root 2, which is times by root 2 on root 2 is 2 root 2. So that is the projection onto here. Now, that, and that's just the length. Oh, sorry, that was supposed to be that length. Whoops. So that was projecting this onto that. So I've used the wrong thing. So I was actually finding this length here, and then in order to find that length, I would use Pythagoras. So my d squared would be my hypotenuse squared, which is root 10 squared, take away what we just found squared. So 2 root 2 squared is 4 2's 8. So we'd get 2. So therefore the distance should be root 2. So how can I fix that up? Yes, so here I said can't always hide, and I put D when I should have put can't always hide. So the adjacent side is the projection side. So I'll just put a little A there, and I'll put a little A here, label it differently. All right, so hopefully you're okay with that error there and you understand that.